school with Professor Prangoski. We'll talk about a brief introduction to the Weyl Hörmander calculus. We will have 45 minutes, 15 minutes break, and after that, 30 minutes. Yes? So
thank you. Just please give me a notice 5 minutes before my time ends.
Of course.
Yes.
I will give you.
Yeah. Okay. Thank you.
5 minutes before.
Yeah, before then. Yeah. Okay. Thanks. So let me just very briefly recall the thing from yesterday. So we were considering simple classes. Which consist of smooth functions, and the idea was, we talked about this yesterday. The idea was that these things generalize the ordinary symbol classes that we all know. So I gave a couple of examples yesterday, how the Schuby classes can be recovered, how the Hörmander S-rho delta classes can be recovered, and then how the general Diels-Pfefferman classes can be recovered from this. And the general idea was that what Hörmander did was he recognized that norm that defines that those spaces boils down to norming the k derivative with respect to a metric. That was the whole lecture from yesterday was in just one sentence that. And okay, so the thing that we realized was that this metric G, from now on I'll just call it by its real name. It's a metric because yesterday I introduced it as a family of inner products. But yeah, that kind of family is just a metric. It has to satisfy certain conditions, so it cannot be totally general. And the conditions that we talked about yesterday, that we found yesterday, were the following three. First, I will write the second and the third one because those were the things that were imposed on the metric by our requirement that the composition of symbols will belong to the symbol classes. So this was the thing from yesterday, the whole messy formulas that we talk about and how these things more or less impose these two conditions. So again, G is a Riemannian metric. So again, for us, this just means that for every point x on R2n, I will denote the points in phase space with capital letters. For every point x on phase space, g of x is an inner product. And it has to satisfy certain additional condition on regularity. So it has to be at least measurable, but for us it's smooth. And the important thing, so this is an inner product. And I introduce one more notation that I will denote the norms, more precisely the square of the norms with respect to this inner product by the same letter. So for me, gx of t is this quadratic form. Because I will mostly use this thing. So this is the length of the vector squared. And now the three conditions were the following. So let's give them the proper name now. This is called temperance. And this says the following, that the quotient so there exists C and N such that this quotient is bounded polynomially with respect to the symplectic dual. And I will write the symplectic dual again. And the trick is that once you have this thing, you immediately have the other quotient. This is a bit tricky to prove it, but you can do it. So once you have this quotient, then you have the other one, the one over this, but probably with a bigger n. But and then I'll just go back and say, okay, I'll take the bigger one, and everything holds. So, so once we have the one quotient, automatically we have the other one. Where this symplectic dual is another Riemannian metric, which is defined like this. So I'll define the quadratic forms, and you will believe me that they are indeed quadratic forms and they are generated by inner products. Just to recall from yesterday, the square brackets denote the symplectic form. So I norm the symplectic form with respect to this inner product. So everything is squared, so this will be a quadratic form, and indeed will come from an inner product. So this G is indeed a Riemannian metric, again. The third one, let me give it the proper name, is called uncertainty principle. My spelling is uncertain. And this says that the metric is always less than its symplectic dual. So this means and just from yesterday briefly, that these two were automatically imposed on us by a requirement that the composition of symbols, the sharp product that we talked about yesterday, will belong in the symbol classes. So we don't have choice there.
So this passing from the metric to the symplectic metric is an evolution. I mean, if you do it twice, you go back to the...
Yes, that was an important thing that I forgot to mention yesterday, and thank you for mentioning it now because I forgot it again. So I'll mention it.
So the control is on both sides, actually.
No, because when you take the symplectic dual, this will switch around, but this is a number, and it will stay.
No, but I mean the third point.
Yes, but it will become the same thing.
Oh, yeah.
Because the symplectic dual of the symplectic dual is the original one, but it will switch the... Yeah, so you cannot gain anything. Yeah, you cannot gain anything. Yeah, thank you for that, because I should mention that thing yesterday, but I forgot. Okay, so the first one, which I didn't give you any explanation from where it came from, and I didn't know. It's a thing that it's imposed on the calculus, probably for technical reasons, so you can construct parametrices, not just parametrices, but to work with the symbols. But I don't have a clear purpose from where it came. For these two, we discussed them yesterday. And the first one is slow variation. And this means that there are R and C. R is supposed to be small, and C is a big constant. So there are R and C, such that this quotient. Sorry. Such that if g of x minus y, but measured with respect to the point x, this is small, then these ratios, so this one or the other one, are all bounded. And notice that the constant is uniform. So this is the slow variation. Okay, so now, because my goal for this part of the lecture is just to show the continuity on S of the operators, because we didn't mention anything about that yesterday, and to show the L2 continuity of the operators that have a bound of just the constant function. So this is the Calderon-Valencourt result. I mean, it's an original form, but of course, for this thing, it's Hörmander's theorem. So now to go back to the symplectic dual, to talk about the thing that I'm supposed to talk about. So first of all, let me, and incidentally, I will also give an examples of when you take a specific metric, what's this symplectic dual, how it looks for the ordinary metrics. Okay, so first of all, let me do one more thing. So if you have a quadratic form, positive definite quadratic form, then let me denote the how I denote it. Let me denote it just G. So it does not depend on X. It's not a metric, just a positive definite quadratic form. Then one can define. Not one can define, but this thing immediately induces a linear map, a linear isomorphism of one Rn. And the induced isomorphism is the following. So G of T is given by Q T times T, where this Q is a linear map. Not just a linear map, but a linear isomorphism. And it is, because this thing is positive definite quadratic form, this Q is symmetric. And it equals to its transpose. So this thing is equivalent thing. So the fact that this is positive definite quadratic form with the fact that there exists such a Q, then la la la. So this is a quadratic symmetric matrix, positive definite. And now the trick is the following: that for any such map, for any such linear map, one can define the symplectic dual of that map, and the symplectic dual, the symplectic dual of that thing, one way to do it is to define it like this. So in the same way, so I'll define the quadratic map G sigma by sup S then Ts squared over G of S, and this will be now again positive definite quadratic form, and of course the map that comes from it, the linear map, is called the symplectic dual of this map Q, and this G is called the symplectic dual of this quadratic form G. This is the one way to define it, but there is another way to define it which is better for calculation. And the thing to do, the other one which is better for calculation is to define the corresponding Q sigma. And as it turns out, that the Q sigma that corresponds to this G sigma is exactly minus sigma, where just to recall, sigma was the linear map which was induced by the symplectic form. So this was the linear map induced by the symplectic form, and we can explicitly give it as a matrix. This is 0, identity, minus identity, 0. These are the identities. This is in a block block representation. So each block here is n by n. So this is minus sigma Q minus 1 sigma. So these two are the same thing. So if you define your G sigma like this, the corresponding Q sigma is exactly this. And now from this thing, one can immediately deduce that if I take the symplectic dual of the symplectic dual, you get the original. And this is easy, but I won't do it because I have to calculate all the minus signs, and I probably messed up somewhere because I probably forget a minus sign. Things won't work out. So I'll leave this thing to check it if you want to check it. But the trick is that if I take the symplectic dual, all the symplectic dual, you end up with the original one. And now the thing is that you can do the same thing with the metric, because the metric is nothing else, just a bunch of quadratic forms at each point, right? I mean, it's the same thing. You just put an X everywhere. You just put an X here, and it's the same thing. So in a sense, you can define the symplectic dual metric of the symplectic dual, and that thing will be the original metric. This is one thing. And the other one about this taking of symplectic duals is the following one. So if I have two forms, let me denote them by two quadratic forms, G1 and G2, and such that G1 is less than G2. This means G1 of T is less than G2 of T. Then when you take the symplectic dual of this thing, the they switch place. So G1 sigma, now G2 sigma of T is less than G1 sigma of T. Okay? So notice that you cannot be fancy here and take again the symplectic dual and get equality. Right? Because if you try to be fancy and take again the symplectic dual, what you get is the original one. Right? Because if I take the symplectic dual, then this will go there, and the sigmas, because there are two, will cancel, and you get the original one. So you won't get anything more. And now this is important because we can use this thing to calculate the symplectic dual metric of the metrics that we talked about yesterday. So instead of doing specifically for the Shubin calculus or the rho delta calculus, let us do it immediately for the general Beals-Pfefferman, and we can deduce from it the symplectic duals of the Shubin calculus and the rho delta and all the others. So I will leave that thing there and just recall that the Beals-Pfefferman metric, from now on I'll just start to call the metrics that they generate the calculus by the name of the calculus. So the Beals-Pfefferman metric was this thing, Gx psi. Now the x and psi are little x and psi because they are right. The whole point x is this. Was dx squared over phi squared plus d psi squared over psi x psi squared. And how we can, and I claim that everything will follow about the symplectic dual from this, because the map Q that corresponds to Gx psi is, let me write it as a matrix. So the map Q of x psi, right, the one that corresponds to Gx psi is, you have the identity here, right, because you have two identities. These are 0, and in front of that you have 1 over phi of x psi squared and 1 over psi of x psi squared. This is your Q, right? And now you just plug here, and don't lazy, and do the multiplication of the matrices, right? Because we know this matrix. I erased that matrix. So sigma was right? So we just multiply. Sigma is this. We multiply it with the inverse, and the inverse of this is just this thing will go up, and then you multiply with again with this thing but with a minus, and you do the multiplication, and you end up with this one. Because you have an inverse here, this thing will go up, but this weird multiplication of sigma on both sides will change places. Will make them to switch places. So this will go up here. And this will be our symplectic dual. So for the Beals-Pfefferman metric, now we can immediately deduce what is the symplectic dual, right? So the symplectic dual metric of the Beals-Pfefferman is psi squared dx squared plus phi squared d psi squared, right? Because this is the part that comes with an x, this is the part that comes with psi, and there are no mixed terms. There's nothing mixed term. If you start with something that does not have mixed terms, you won't get anything with mixed terms. So let me just write it here. I can erase this thing because yeah. So the symplectic dual this is the symplectic dual. Yeah, you can immediately read it from this. Okay. And now this is interesting because now we can really see the geometric reason why the Beals-Pfefferman calculus and all these other calculi, this phi and psi when you multiply them together, have to be bigger than 1. Have to be bigger than a constant. Yesterday, that thing I just mentioned it and somehow put it under the rug, right? I just said they have to be bigger than a constant, the product. But now the geometric reason is that if you want for this thing to be less than this, so this is the uncertainty principle, this automatically will force the fact that phi times psi is always bigger than a constant. Right? So, for example, just in this metric, so for this thing to hold, just substitute the vector, it doesn't matter which one, you just substitute, for example, substitute the vector that has 1 as a first coordinate and everything has L zeros. Right? So if I substitute gx psi 1 and then la 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 zeros, this has to be smaller than a 1 and la la zeros. And then you have 1 over phi squared less than, right? You have this, then you multiply, you do the simplification, and what you get? And not just that, but you can do the other way around, that if this thing holds, then the uncertainty principle holds. So this is equivalent reformulation of the uncertainty principle. And this is the reason why in all the calculus that you know, always the key assumption is that the product of the two weights has to be bigger than a constant, because this is just this thing here. Notice that even in the Hörmander rho delta calculus, this thing holds, right? Because, let me write that thing. So the Hörmander rho delta calculus corresponds, because, maybe this is good to write it down. So for the Hörmander rho delta, these were the symbol classes this thing was the weight, m, and the metric that would generate this calculus is the Bill-Sefferman metric there, where this is phi, this is psi, right? So the corresponding metric, the rho delta metric, is psi to the power 2 delta, because it's minus, so it will be upstairs. Right? This is the rho delta metric. And if you want to check the uncertainty principle, the uncertainty principle is exactly this. Psi to the power 2 rho, not 2 rho, I don't need the 2, times psi to the power minus delta, right? Because it's, which automatically implies rho bigger than delta. That's the assumption of the calculus. The other peculiar assumption about delta being less than 1, you know that in the rho delta calculus you have to assume that delta is less than 1 also. That thing will come from the temperance condition, but I won't show it. So if you want to show that that metric is temperate, this condition here will automatically force you to assume that delta is less than 1. Okay? So, so this is our metric. I mean, not the general metric now. And one more thing, one has to impose conditions on the weight. It cannot be totally general. I didn't mention this yesterday, but now you have to believe me on this, that this weight, m, of course has to be positive, but it has to satisfy something like these two conditions. So it has to be slowly varying in a sense with respect to the metric, and it has to be temperate with respect to the metric. The temperance can be, I can easily more or less explain it to you, because this will somehow imply that the weight cannot grow faster than a polynomial. which is something that you can have to impose if you think about it, because otherwise your spaces won't be a subspaces of S prime, right? Because you want your symbol classes to belong to S prime. So for the condition on M, again, slow variation. And this is exactly the same thing as here. So I'll copy. There are R and C such that this implication holds. If X and Y are close to each other, then the ratios of M of X over M of Y are bounded. So this, again, this is the same thing as here. And the other one is temperance. So this is, there exists C and N. And again, if you have one of the ratios, then you can show that the other one also holds. And I have to check both of them, but the constant will be a bit bigger. There. So these are the conditions, and the SMG class, I wrote it yesterday, but let me do it again. SMG consists of all smooth functions such that we norm the differential. Right, that was the thing. We normed the differential with respect to the metric. This thing should be bounded. It's supremum over X, of course. Otherwise, yeah, supremum over X. This thing should be bounded for all A. And this family will produce seminorms, and SMG will become a Frechet space. You have a countable family of seminorms, and SMG will become a Frechet space. Ah, yeah, I forgot the M, right? There is no M here. Aha. There should be an M. Sorry. There should be an M. So this thing has to grow like M. So there should be an M here. This is the growth of the symbol. Yeah, otherwise it makes no sense. Okay, so these are our classes. And we talked about yesterday how this, I mean, even now, how this thing reduces to the ordinary symbol classes. Okay, so the first thing now is to show the S continuity, and also the L2 continuity of the symbols is in S1G. So let me do first what do I want to do first?
Sorry? Excuse me, in the definition below, where you have the product of GX, what is this comment?
One half.
Ah, one
because I had to divide with the length of the vector. Okay. And Gx is the square of the length of the vector, so yeah.
Okay.
So that. Probably it's better to do first the L2 continuity. So let us do first the L2 continuity. But for that thing, okay, so now I will need one additional construction. This thing has nothing to do with the calculus now, but it is a very convenient tool to use it. And I think that the L2 continuity is the best place to show in a certain way how to use this tool. So this is essential, not essentially, but it is really due to Pomny and Lerner. This is their construction. Hörmander does this thing in a slightly different way. But I'm more accustomed to this construction because I've used it more than the construction on Hörmander. So the trick is to, so if you have a symbol, so let me talk about the general idea first. The trick is that if you have a symbol, A of X, the idea is to construct a family which will localize the symbol in phase space, because this lives in phase space, to localize the symbol in phase space and to represent it as a sum. So instead of writing A of X, to write it like A of X times phi j of X, where this phi j are in D are 2n now, and they are essentially cutting the symbol, but the way they are cutting the symbol is such a way that the volume with respect to the metric stays the same. So if your metric, let's just for a moment assume that your metric is the flat metric, the Euclidean, then what you use here, then you use just translation of a single cutoff function. Because if you take one single cut, function just that cuts something in a volume, a ball, and you just use the translates of that thing will always cut the same amount of volume with respect to the Euclidean norm, right? But the phase space is not Euclidean. It's never Euclidean, right? Because the metric is the thing that will generate the calculus. So I want a family which will cut, in a certain sense, the same amount of volume everywhere. And now the idea of this construction, technically Hörmander uses this kind of thing. So he uses a family, he constructs such a family, which will cut the symbol in pieces, and then you analyze each piece separately. Because if you think about it, this piece is a function in DRN now, automatically in SRN, so it's easy to analyze it. But what Bonnier and Lerner do is, instead of looking at a family of a count of a family, they look at a family which is parameterized by the points of Rn, and instead of looking at sums, they look at integrals. And the integrals, it turns out, at least for me, that they're easier to work with. So the definition is the following. So let me put one more notation here. UXR, for me, will be from now on, UXR, this is in phase space now, capital R, is the point of all y in Rn, not Rn, but R2n, which are at distance r from x, but measured with respect to this x. Again, this just means that y belongs to the ball with radius r, but I measure the ball with respect to the metric at x. So this thing will change the sizes and the volumes everywhere, right? But when you calculate the volume of this thing, but the volume with respect to the volume form of the metric, they all have the same volume. Okay? And now, the definition is the following. So I have phi in SR2n. I define this semi-norm on it.
Sorry, just a question. Then you can estimate the volume of this ball?
Yeah, you can calculate it. I can just. This is the volume form of the metric. So this will become something like this, right? So this is dy. Okay? And now the trick is, now I'll do something weird here, is the following thing. So this gy, because again, now I will use the temperance. The metric, when because this r is small, on this set, g of x is the same as g of y, modulo constant. So that means that the determinant will also be modulo constant, the same thing as the determinant at x, right? So I'll put here an x, and then you just change variables there, right? Because this thing is just g of x of y less than r squared when you change variables. And then this is just change of variables. And this is just whatever the volume of the ball is. I don't know what's the volume of the ball. Right? It's r squared to the whatever power times pi, whatever, and so on. Right? So all I'm saying is that these balls have more or less the same volume because of this. Again, they don't have the same volume because there is an extra constant that will pop from here. This constant. Right? Because this constant will pop from the change of the determinant here. Because I change it from gy to gx. But they are bounded by the same thing.
So this is one of the reasons of the slow variation.
Yes, this is one of the reasons, but I cannot give you, because this is not a good reason for me. A good reason was the thing that I showed you yesterday about this thing, where you can really see what's the problem about the composition. This is like a thing that pops up somehow, but I don't know. It doesn't matter. That's a philosophical discussion. The point is that this thing has more or less the same volume. That's the upshot. So this is a norm now, not a norm but a semi-norm. So I norm the L differential, L, because okay, I have to take the supremum over L less than K to be a semi-norm. And then I take the L differential, Y, again, norm it. But again, instead of, if I wanted to do as a symbol, I will norm it with respect to gy, but now I will norm it with respect to gx. Times y. So x is fixed. So let's talk about this. So I fix x. When you fix x, this thing here is just the distance from y to the set, to this set, right? Because x is fixed. This is just a distance. It's a Euclidean distance. Of course, it depends on x, but if you forget about the x because x is fixed for the moment, this is just a Euclidean distance from y to the set, and this is just an ordinary seminorm on the space S, right? Because the seminorms on the space S are derivatives, and then you multiply with the Euclidean distance. This is just an ordinary seminorm on Rn. But now I have a whole family of seminorms, parameterized by x. When I have one fixed, when I have a phi, for each phi in S, I can define this seminorm. Of course, if I try to move the x around, these norms will start to explode. Okay?
I
So
have a question.
the idea is the following. Instead of looking, because again, instead of looking one phi, the idea is to look a family of phis, each one parameterized by x, such that for this norm will be finite.
One cup.
Hmm?
One cup.
Sorry?
One cup.
1/2? What?
You have 5 minutes.
Oh, have fine.
No, denominator. One cup.
Yeah, you always assume there is a half. So again, the idea is, I will finish with this. The idea is now that instead of one phi, I have a family of phis, parameterized by x. So for each x, I have one phi for which I take this seminorm of it. Okay, so I have a whole family. And this family will move to the, how the x moves, this thing will move to the phase space and will always, this thing will say that away from this ball u of x, this will decay rapidly. And it decays uniformly in a sense rapidly. So if I take here, the rapid decay will be the same as if I take there, the rapid decay also of it. And this construction of Bonnier and Lerner is really brilliant because this makes the calculus to work. So now instead of one phi, I have a family of phis. of x of i's, each one with this parameterized backs, the whole family parameterized backs, and instead of looking this semi-norm, for each x I norm it like this, and then I take the supremum of x. And I denote this thing, let me call it, this is a notation that it's not good, but I will use it because it's somehow suggestive. This is the family phi of x, and I will write conf because the name of these things, that Bonnier-Lerner, these things are called the Bonnier-Lerner confined family of symbols, a uniformly confined family of symbols. I'm finishing in 1 minute.
You have 5.
Thank you. So, a family phi of x, parameters of x, is called uniformly confined family of symbols if for each x I can norm them like this and take the supremum and it's finite. And now this is weird. Why there exists such a thing, and there exists, and the construction is very simple. And it's not just that it's very simple, but it's very useful to have that family, and I will always work with that family from now on. So let me now not make a stupid mistake. So I take high not in C infinity R, so just one variable. High not is non-decreasing, no, not increasing. It has a support in 0, 1. It is non-negative. And restricted to 0, 1/2 is 1. So this is something like this. A lot of words for something like this. Aha. So in R plus. So only from here onwards. I don't care anything about it.
Sorry to interrupt. Someone in Zoom is asking you the following. In the semi-norm definition, the multilinear derivatives are taken with respect to the Euclidean metric, right?
The semi-norms here.
Yes.
No, the metric is not Euclidean here.
The derivatives, he said.
Aha, the derivatives, yeah. The derivatives.
And then he says, but the growth estimates are in terms of some other metric.
Yes.
I am asking this because the definition of the gradient, at least k equal 1, in seminar definition changes if the metric changes.
Yes, but no. So again, the definition is of the derivative of derivatives is the ordinary Euclidean one. So again, the definition of the derivative is the ordinary Euclidean one. I norm them with respect to this family of inner products or family or the Riemannian metric.
Okay, thank you.
So my G I define my psi of x like this. And now, because this has support in 0, 1, this automatically means that the support of psi x is here. So the whole support is here. Okay, and one more thing I will do. If you take the integral, with respect to the volume form, turns out that this is always positive. So if I define my function omega y like this is always positive. So it makes sense to take 1 over omega y. This is well defined in sin infinity. And now I define my, the family of Bonian Lerner, which is and the trick about this thing is these things for it's the all finite, because when your y is outside of u of xr, this is 0 because of this. So the only place where this thing is non-zero is only when y is inside of u of xr. So this thing is just 1 there, and everything outside is 0. So it's really confined in the ball u of xr. And one more thing, that because of this construction, if I take the integral with respect to the volume form, this is 1. And now I will make a break, because later on I will just use this family. All the time I will use this family.
Okay.
Questions? Yeah, or maybe.
Okay, thank you. So maybe questions. Maybe we have 2 minutes for questions. So questions for Bojan? No? I have one question, but maybe did you want to consult a continuous partition of unity or something?
Sorry, again?
Do you want to consult a continuous?
Yes, a continuous partition of unity. Yes.
Okay.
Yes.
Okay, so
But the trick again, so this is the partition of unity. It's a continuous partition of unity, but the trick for me is, this is the more important part, is that they're not confined, but have support in a uniform way in these balls.
okay.
So each phi of x has support in the u of x.
Okay. Thank you. So we have a 15 minutes break now before.
Yes. Okay, thanks. Okay.
Hope you can, yes.
One more.
Interesting.